This is the second session that describes gas exchange and transport. The learning objectives are to describe the transport of oxygen and explain the clinical application of today's lecture. Starting with the oxygen transport, we have to know that the oxygen is transported in the blood in two forms. Physically dissolved form, which is the physical form, and attached in a loose chemical combination with the hemoglobin, which is the chemical form. The physical form of oxygen represents the free oxygen molecule dissolved in the blood. In the arterial side, it's 0.3 milliliter per 100 milliliter of arterial blood, while in the venous side, it's 0.1 milliliter per 100 milliliter of the venous blood. So in the whole blood, which is 5 liter, the oxygen present in the physical form is 15 milliliter. This is far low compared with the oxygen requirement per minute in an adult man, which is 250 milliliter. So the physical form of the oxygen is not enough to supply the tissue need, and we need another form to supply it, which is the chemical form. So what is the importance of the physical form of oxygen? It is important as it determines the oxygen tension, that's to say the partial pressure of the oxygen in the arterial blood. And this oxygen tension or partial pressure of oxygen in turn determines the rate and direction of diffusion of the oxygen and the percentage saturation of hemoglobin with oxygen. That's to say, the oxygen in the physical form determines the oxygen in the chemical form. The chemical form of oxygen represents the oxygen that combines with the ion of the hemoglobin while still in the ferrous state. In the arterial side, it's 19 milliliter per 100 milliliter of arterial blood, while in the venous side, it's 14 milliliter per 100 milliliter of the venous blood. This amount depends on the oxygen tension. That's to say, this volume will decrease with decreased partial pressure of oxygen. Hemoglobin is a remarkable compound made up of 4 polypeptide chains, each with an attached heme moiety. The heme molecule consists of a porphyrin ring with one atom of ferrous ion in the center. Each of these 4 ferrous atoms can reversibly combine with one molecule of oxygen. The iron molecules remain in the ferrous state when they bind with oxygen. Thus, the reaction is considered oxygenation, not oxidation. It's important to know that oxygen combines with hemoglobin in steps, forming intermediary compound as you can see here. The binding of hemoglobin with the first molecule of oxygen facilitates the next binding and so on till full saturation occurs. So, what is the importance of the chemical form of oxygen? Well, the chemical form of oxygen constitutes the main supply of oxygen to the tissues. It is to be noted that tissues must utilize oxygen in the physical solution first. This leads to drop in the oxygen tension in the arterial blood, and therefore the oxygen will be dissociated from the hemoglobin to supply the tissues. While discussing oxygen transport, it's important to emphasize on certain important terms. First, oxygen content. Oxygen content is the volume of oxygen carried by blood combined with hemoglobin per 100 milliliter of blood. It's expressed in units of volume percent, that's to say milliliter oxygen per 100 milliliter of blood. The oxygen content depends on the amount of hemoglobin present, the oxygen tension, the hemoglobin affinity for oxygen, and the metabolic state of the organ. The second important term is the oxygen capacity of the blood. The oxygen capacity of the blood is the maximum volume of oxygen that can be carried by hemoglobin when the hemoglobin is fully saturated with oxygen. It's important to know that the 1 gram of hemoglobin can combine with 1.34 milliliter of the oxygen when it is fully saturated. And we all know that the average amount of hemoglobin in the blood is around 15 gram. So the oxygen capacity of the blood will equal to 15 times 1.34, which will give us 20 milliliter. This calculation reveals that the oxygen capacity of the blood depends on the amount of hemoglobin and does not depend on the oxygen tension. The last important term is the percentage saturation of hemoglobin with oxygen, which can be calculated by the equation that states that oxygen content divided by oxygen capacity times 100 will give us the percentage saturation of hemoglobin with oxygen. It's important to note that this percentage does not depend on the amount of hemoglobin, but depend on the oxygen tension. So, in cases of anemia where there is reduction in the amount of hemoglobin, there is decrease in both the oxygen content and the oxygen capacity, so accordingly the percentage of saturation is not affected. Now let's see how oxygen is delivered to the tissue. The amount of oxygen delivered to the tissue is determined by the blood flow and the oxygen content of the blood. In terms of the whole body, the blood flow is considered to be the cardiac output, and the oxygen content of the blood is what we discussed earlier. It's the sum of the dissolved oxygen, representing 2%, and the chemical form of oxygen in the hemoglobin, representing 98%. So the oxygen delivery equation will equal to cardiac output times the oxygen content of the blood. Now, after knowing that the oxygen content of the blood is the sum of the dissolved oxygen, the physical form representing 2%, and the chemical form of oxygen in the hemoglobin representing 98% of the oxygen, and knowing that the physical form of the oxygen is giving us the partial pressure of the oxygen or the oxygen tension, which is responsible about the chemical form of the oxygen inside the hemoglobin, let's see how these factors relate to each other and explain the oxygen delivery to the tissue. To start with, we'll explain the oxygen hemoglobin dissociation curve. The oxygen hemoglobin dissociation curve shows the relationship between the oxygen tension, which is the partial pressure of oxygen, and the percent saturation of hemoglobin with oxygen. It's an S-shaped curve due to the fact that oxygen combines with hemoglobin in steps as mentioned earlier, and each step increases the affinity of hemoglobin to oxygen in the next step until the maximum saturation occurs. Note that the affinity for the fourth and the last molecule of oxygen is the highest and occurs at values of partial pressure of oxygen between 60 to 100 mm mercury, where the saturation is nearly 100%, corresponding to 4 molecules of oxygen per 1 molecule of hemoglobin. This phenomenon is described as positive cooperativity. A significant point on the oxygen hemoglobin dissociation curve is the P50. By definition, P50 is the partial pressure of oxygen at which the hemoglobin is 50% saturated. That's to say, where 2 of the 4 heme groups are bound to oxygen. A change in the value of P50 is used as an indicator for a change in the affinity of hemoglobin for oxygen. An increase in the P50 reflects decrease in the affinity and represent shift to the right of the oxygen dissociation curve. And a decrease in the P50 reflects increase in the affinity and represent shift to the left in the oxygen dissociation curve. To start with, let's explain the oxygen hemoglobin dissociation curve. The oxygen hemoglobin dissociation curve shows the relationship between the... Now let's describe the curve at the level of the lung. In the lung, the partial pressure of oxygen is 100 mm mercury. Hemoglobin is nearly 100% saturated. That's to say, all heme groups are bound to oxygen. Due to positive cooperativity, the affinity is the highest and the oxygen is most tightly bound, giving us the flat portion of the curve. The flat portion of the curve extends from 100 mm mercury to 60 mm mercury, which means that human can tolerate substantial decrease in alveolar partial pressure of oxygen to 60 mm mercury, such as in cases of decreased atmospheric pressure, such as in the high altitude, without significantly compromising the amount of oxygen carried by hemoglobin. Note that when the partial pressure of oxygen is 100 mm mercury, representing normal alveolar partial pressure of oxygen, the hemoglobin is 97% saturated with oxygen. Whereas when there is decrease in the partial pressure of oxygen up to 70 mm mercury, representing a state of high altitude, the hemoglobin is 90% saturated with oxygen. This decrease in the partial pressure of oxygen occurs in the horizontal part of the curve. That's to say, marked decrease in the partial pressure of oxygen cause little changes in the percentage saturation of hemoglobin with oxygen. And this is because at high oxygen tension, the hemoglobin has higher affinity for oxygen. Now, looking at the curve at the level of the tissue, at the tissue, we'll find that oxygen is easily and rapidly dissociated from hemoglobin to pass to the tissue, where the partial pressure of the oxygen become 40 mm mercury during rest and 20 mm mercury during exercise. This occurred in the steep part of the curve. So, little decrease in the partial pressure of oxygen at the tissue causes marked decrease in the percentage saturation of hemoglobin with oxygen to give more oxygen to the tissue. Note that when the blood reaches the resting tissue, the partial pressure of oxygen is 40 mm mercury and the hemoglobin is 70% saturated with oxygen. During tissue activity, the partial pressure of oxygen dropped to 20 mm mercury and the hemoglobin is 40% saturated with oxygen. Thus, with increased tissue activity, an extra 30% of oxygen given to the tissue with little decrease in the partial pressure of oxygen. And this is because at low partial pressure of oxygen, the hemoglobin has low affinity for oxygen. Now, let's discuss the causes of shift to the right in the oxygen hemoglobin dissociation curve. But before discussing the causes, we should know what does it mean to say shift to the right in the oxygen hemoglobin dissociation curve. It means that at any given partial pressure of oxygen, hemoglobin will be less saturated with oxygen. So, more oxygen will be given to the tissue. That's to say, the affinity of hemoglobin to the oxygen is decreased, leading to unloading of the oxygen content in the hemoglobin to the tissue. So, this increased the oxygen supply to the active tissue. What are the causes of shift to the right in the oxygen hemoglobin dissociation curve? Number one, increase in the partial pressure of carbon dioxide. It's a state of acidosis, represented as decrease in the pH. Another cause is the increase in the temperature or increase in the level of 2,3-diphosphoglycerate. We said earlier that the increase in the partial pressure of carbon dioxide, which is a state of acidosis represented as a drop in the pH, shows a right shift in the oxygen hemoglobin dissociation curve. This means that at any given partial pressure of oxygen, hemoglobin will be less saturated with oxygen, so more oxygen will be given to the tissue. This is due to the fact that the presence of carbon dioxide and hydrogen ion combine with sites on hemoglobin, changing its configurations and facilitating the unloading of oxygen. The purpose for this is to provide more oxygen to the tissue when the metabolic rate is increased. We can see this during muscle exercise, where there is accumulation of carbon dioxide accompanied by increase in the partial pressure of carbon dioxide, a state of acidosis represented as a drop in the pH. This will lead to unloading of the oxygen from the hemoglobin to the tissue to meet the tissue need. The effect of the change in the partial pressure of carbon dioxide on the oxygen hemoglobin dissociation curve is known as Bohr effect. The increase in the temperature shows right shift in the oxygen hemoglobin dissociation curve. This means that at any given partial pressure of oxygen, hemoglobin will be less saturated with oxygen, so more oxygen will be given to the tissue. So the rise in the temperature is accompanied by decrease in the hemoglobin affinity for the oxygen, facilitating the unloading of the oxygen from the hemoglobin to the tissue. The effect of 2,3-diphosphoglycerate on the oxygen hemoglobin dissociation curve is the increase in the concentration of 2,3-diphosphoglycerate shows right shift in the oxygen hemoglobin dissociation curve. The 2,3-diphosphoglycerate is the end product of the anaerobic glycolysis in the RBCs. The concentration of 2,3-diphosphoglycerate can increase in state of hypoxia accompanying the presence of the high altitude, or during muscle exercise, or in certain cases of anemia. Like carbon dioxide and hydrogen ion concentration, 2,3-diphosphoglycerate facilitate the unloading of oxygen from the hemoglobin, as this substance combines with the hemoglobin in deoxygenated form, so it decreases the hemoglobin affinity for the oxygen, make it easy for the unloading of oxygen from the hemoglobin to the tissue to meet the tissue need. Remember that the causes of shift to the right in the oxygen-hemoglobin dissociation curve include increase in the partial pressure of carbon dioxide, drop in the pH, increase in the temperature, increase in the concentration of 2,3-diphosphoglycerate. All these factors are available during muscle exercise. During muscle exercise, there is accumulation of carbon dioxide with increase in the partial pressure of carbon dioxide, drop in the pH, increase in the temperature, increase in the concentration of 2,3-diphosphoglycerate. The presence of these factors facilitate the unloading of the oxygen from the hemoglobin to the tissue to meet the tissue needs. Now we will discuss the causes of shift to the left in the oxygen-hemoglobin dissociation curve. Before discussing the causes, we should know what does it mean to say shift to the left in the oxygen-hemoglobin dissociation curve. It means that at any partial pressure of oxygen, hemoglobin will be more saturated, so less oxygen will be given to the tissue. That's to say, the affinity of hemoglobin for oxygen is increased. That's to say, hemoglobin is being loaded with oxygen and giving the oxygen to the tissue with great difficulty. The causes of shift to the left include decrease in the partial pressure of the carbon dioxide, increase in the pH, decrease in the temperature, decrease in the concentration of 2,3-diphosphoglycerate, also the presence of the fetal hemoglobin, and carbon monoxide poisoning. Now it is important to know that adult hemoglobin contains a pair of alpha and a pair of beta polypeptide chains. The beta polypeptide chains can combine with 2,3-diphosphoglycerate, the end product of the anaerobic glycolysis in the RBCs. This combination decreases the affinity of the adult hemoglobin to oxygen, while the fetal hemoglobin contains a pair of alpha and a pair of gamma polypeptide chains. The gamma polypeptide chains cannot combine with 2,3-diphosphoglycerate. This increases the affinity of the fetal hemoglobin for oxygen. Thus, shift the curve to the left. Note that the decreased affinity of the adult hemoglobin for oxygen and the increased affinity of the fetal hemoglobin for oxygen facilitate the movement of oxygen from the mother to the fetus. Now, what is the effect of carbon monoxide poisoning on the oxygen-hemoglobin dissociation curve? Well, carbon monoxide combines with hemoglobin to form carboxyhemoglobin and cause shift of the oxygen-hemoglobin dissociation curve to the left. This is because that the affinity of carbon monoxide for oxygen binding site on hemoglobin is more than 200 times greater than that of oxygen. The cause of this shift is that most of the oxygen binding sites are occupied by carbon monoxide molecules that don't respond to decrease in the partial pressure of oxygen level, and the oxygen molecules that remain are strongly bounded to the hemoglobin and not easily unloaded to the tissue. Now always remember the difference between shift to the right of the oxygen hemoglobin dissociation curve and shift to the left of the oxygen hemoglobin dissociation curve. Shift to the right means that at any given partial pressure of oxygen, hemoglobin will be less saturated with oxygen, so more oxygen will be given to the tissue. It's a state of unloading. While shift to the left means that at any partial pressure of oxygen, hemoglobin will be more saturated, so less oxygen will be given to the tissue, so the hemoglobin will be loaded with oxygen. As we finish the oxygen hemoglobin dissociation curve, it's important to discuss the oxygen dissociation curve of myoglobin. Remember that hemoglobin has 4 ferrous atoms, each of which can combine with one oxygen molecule. So, one molecule of hemoglobin can combine with 4 molecules of oxygen. On the other hand, Myoglobin has one ferrous atom, which can combine with one oxygen molecule. The oxygen dissociation curve of myoglobin is a rectangular hyperbola. That's to say, it remained horizontal till very low oxygen tension, then suddenly descend vertically. It does not give its oxygen easily except at a very low oxygen tension. For example, during severe muscle exercise, when the hemoglobin has given most of its oxygen. So, myoglobin acts as an oxygen store to be used by muscles when the oxygen tension becomes very low in tissue, as in severe exercise. After exercise, the myoglobin sucks the oxygen from the blood to form an oxygen store again. Note that neither the hemoglobin nor the myoglobin can carry the function of each other. Also, it's important to know that the difference between the two curves is due to the capacity of the hemoglobin to form an intermediary compound with the oxygen, while myoglobin combine with one molecule of oxygen only. Myoglobin is either fully saturated during rest or fully dissociated during exercise. What could be the clinical application of today's session? The cases of anemia has a clinical application for today's session. As in anemia, there is a reduction in the amount of hemoglobin, which is accompanied by decrease in both the oxygen content and the oxygen capacity, and accordingly, the percentage saturation of hemoglobin with oxygen is not affected. Muscle exercise is another clinical application for today's session, as during muscle exercise there is accumulation of carbon dioxide, accompanied by increase in the partial pressure of carbon dioxide, showing a state of acidosis represented as a drop in the pH. There is increase in the temperature. There is increase in the concentration of 2,3-diphosphoglycerate. All these factors lead to shift to the right in the oxygen hemoglobin dissociation curve, making it easy for the hemoglobin to unload the oxygen to the tissue to meet the tissue needs. Carbon monoxide poisoning is another clinical application of today's session. Presence of carbon monoxide leads to shift to the left of the oxygen hemoglobin dissociation curve. So the presence of carbon monoxide has a catastrophic effect on the oxygen delivery to the tissue. Not only there is reduction in the oxygen binding capacity of the hemoglobin, but also the remaining heme sites bind oxygen more tightly, making it very difficult for the hemoglobin to unload oxygen to the tissue. Fetal hemoglobin is another clinical application of today's session. Fetal hemoglobin shifts the oxygen hemoglobin dissociation curve to the left. Fetal hemoglobin has high affinity for oxygen in comparison to the adult hemoglobin that has low affinity for oxygen. This facilitates the movement of oxygen from the mother to the fetus. By this, we finish today's session. I hope you enjoyed it. Thank you.